All right, guys, so I want to do Gauss's law with a gravitation example, see if we can come up with the gravitational force equation. So if I were to set up the Gauss's law equation the same way that I do for electrostatics, which is a surface integral of the field dot dA, right? So dot some area vector of some Gaussian shape that you're going to draw. Gravitational field, we just use little g, right? That's our 10 meter per second squared at the surface of the Earth. That's just gravitational field strength. So surface integral of g dot dA is equal to, well, we are now doing gravitation. So we're replacing electrostatics terms with gravity terms. So in electrostatics, we talk about charges creating fields. Now in gravitation, we'll talk about masses creating fields. So I have the amount of mass enclosed divided by, well, in electrostatics, we had epsilon naught, which was the permittivity of vacuum. So I'm just going to use epsilon naught, which is basically some gravitational constant that describes how gravitational fields are held in space. I don't know if there's different material that could hold gravitational fields differently, like electric fields can be. We know that some insulators are good at like polarizing, and they have a different permittivity. Let's just come up with a generic epsilon term for gravity, okay? So I would, if this were maybe something like a sphere, maybe it's like a planet who has a mass of big M, I would expect there to be a spherical symmetry to the gravitational field, right? All the gravitational field lines would point towards the center, kind of like a negative charge in electrostatics. So I would draw a Gaussian sphere, and if R is greater than big R, then I would expect that I contain the entire mass of the planet. And because of this spherical symmetry, the surface integral just becomes, if it's g dot dA equals mass enclosed over epsilon naught, then this surface integral would be just g times the A of my Gaussian is equal to the amount of mass enclosed. Well, if R is bigger than R, then I've enclosed all of the mass. So I have mass over epsilon naught. And because I have a Gaussian sphere, the area of that sphere is just 4 pi r squared. That's equal to the total mass divided by epsilon naught. And then just like I did in electrostatics, I would solve for the field strength G. So the gravitational field strength G is equal to the total mass of the planet divided by 4 pi r squared epsilon naught. But this is looking a lot like the electric field of a point charge, right? Where 1 over 4 pi epsilon naught, I'm going to want to name that after somebody. So I'll go ahead and call 1 over 4 pi epsilon naught, let's call that capital G, the universal gravitational constant. So the gravitational field outside of a planet is just gm over r squared. No big surprise there. We've been using that for quite some time, right? G times the mass of the planet divided by how far you are from the center of the planet squared. So that's our little g. But what happens when you're inside of the planet, when r is less than big R? So I can set up my surface integral of g dot dA, and I'll set that equal to the amount of mass enclosed divided by epsilon naught. By the way, this would be called gravitational flux, right? So the amount of mass enclosed divided by epsilon naught is just the gravitational flux. The surface integral, again, is pretty simple. It just becomes g a Gauss. The difference now is the amount of mass that I capture is not the total mass. It will instead be the density times the volume of my Gaussian. So I have density times volume of the Gaussian divided by epsilon naught. The volume of my Gaussian, again, because it's a sphere, is 4/3 pi r cubed. Density, assuming that this planet has a uniform density, then I could say that the density is the total mass divided by the total volume, or total mass divided by 4/3 pi big R cubed. Okay, so my surface integral, G times the volume of, or sorry, the area of my Gaussian shape, 4 pi r squared, is equal to the density, which is mass over volume, 4/3 pi big R cubed, times the Gaussian volume, which is 4/3 pi little r cubed divided by j epsilon naught. And if I want to get the gravitational field by itself, I will go ahead and divide over the 4 pi r squared. Let me do some canceling before I do that. I see a 4/3 and I see a pi, so I'll get rid of those. And then I have just m r cubed over, I'm bringing over 4 pi r squared, so 4 pi r squared, and then I still have a j epsilon. So again, I see my 1 over 4 pi j epsilon naught. So 1 over 4 pi j epsilon naught I know is just capital G. Then I have the total mass of the planet, but instead of gm over r squared, inside of the planet I get something weird. R cubed over r squared is just r to the first. So the gravitational field strength inside of a planet is not proportional to 1 over r squared like I might have expected. It's actually linear. It's proportional to r. Now that is actually really interesting because for a very long time we probably have had a gut feeling that if you were to drill a hole through the center of the earth and maybe you just jump through it, then you would probably oscillate back and forth, right? And we might even suggest that this is simple harmonic motion. But the idea that the force on you is gmm over r squared is actually a problem, and it doesn't make sense intuitively. If we think that you're going to oscillate back and forth, what would happen to you when you're at the center of the planet? Well, if you put in 0 for radius or distance to the center of the planet, then you get an infinite gravitational force. So if you were to jump into that hole, then you would be stuck in the middle forever and nobody could ever pull you out according to this equation. Obviously that doesn't make sense because we know that you would have so much kinetic energy built up that you would fly past that position and then you would start to slow down. So this proportional to r force actually makes a lot more sense, because if the gravitational force inside of the Earth is, or at least the gravitational field strength is gmr, then at the center of the Earth, you have no gravitational force. Gmr, r being 0, it would eliminate your gravitational force until you pass that center point, and then it starts to try to pull you back. So let's check, is it really simple harmonic motion? Well, we know that the gravitational force is just mg, and it's an attractive force, so we put a minus there. So m is your mass, g is the gravitational field strength, and since I'm jumping into this hole in the Earth, I'm going to use the gravitational field strength inside of the Earth, which is our gmr. So we'll go ahead and take minus m times gmr. And I'm seeing a gravitational force that is both restoring and proportional to the displacement to the first power. So that's interesting because that is our condition of Hooke's law. And when we have a net force that follows Hooke's law, we know this object is in simple harmonic motion. And if it's in simple harmonic motion, then we can use the acceleration. So Fg is just ma, so I'll divide by your mass, and we get just gm times r. So if the acceleration is both linear and restoring, then we have simple harmonic motion where the constant in front of our displacement to the first power, gm, is just omega squared. So omega is the square root of g times the mass of the Earth. We know the period of this simple harmonic motion is just 2 pi over omega. So if you want to know how long it would take you to come back, if you jump through that hole through the center of the Earth, it's just 2 pi over the square root of g times the mass of the Earth. So maybe let's try to get that in hours and figure out how long that would take. All right, so that should be it. I got a class coming in. They look excited. Video 1.